The morning sun hung low over the Solomon Islands on January 5, 1943, casting long shadows across the steel decks of American warships cutting through the waters of Kula Gulf. Lieutenant Red Cochrane stood at his post aboard the cruiser USS Helena, hands gripping the fire control director with practiced tension, eyes tracking four dark shapes descending through scattered clouds. The Japanese dive bombers, Aichi D-3A aircraft that Allied forces had designated with the code name VAL, had completed their attack run against the American task force with characteristic precision. These aircraft had just released their bombs against the New Zealand cruiser Achilles, and now they banked away in formation, their pilots confident they had survived another mission against the American fleet. Cochrane's fingers moved across controls that armed shells containing technology unlike anything the Japanese High Command could imagine, technology that would fundamentally rewrite the mathematics of aerial warfare within the next 30 seconds. The order came through ship communications. Fire. 2 salvos thundered from Helena's aft 5-inch battery, the concussion rolling across the water in waves of pressure that rattled equipment throughout the ship. Cochrane watched through optical equipment as shells arced upward toward the departing Japanese formation. One of the Japanese aircraft suddenly erupted in flames without any visible impact, the VAL disintegrating as though struck by an invisible hammer, ripped apart by shrapnel from a shell that exploded 30 feet away from the fuselage. The pilot, a young man who had survived missions against American forces for months, never understood what killed him in those final seconds. His wingmen saw the explosion and the death of their comrade, but could not comprehend the nature of the weapon that had found them. Neither would the Japanese High Command understand, not for the remainder of the war, despite capturing examples and conducting technical analysis. This was the first combat kill by a weapon that military historians would later rank alongside radar and the atomic bomb in strategic importance during the Second World War. The proximity fuse, deceptively codenamed the variable time fuse or VT fuse by Allied forces seeking to protect its true nature, had just announced itself to the Pacific War in that moment of fire and destruction over Kula Gulf. Over the next 2.5 years, as American forces advanced across thousands of miles of ocean toward Japan, this technology would fundamentally alter Japanese tactical calculations, shatter their aerial offensive capability, and save thousands of American lives through mathematics that enemy forces could not counter and barely understood even when they examined captured examples. The transformation that began that morning had its roots not in brilliance or genius, but in a fundamental problem that had plagued anti-aircraft gunners since the moment military planners first recognized that aircraft represented weapons of war rather than curiosities of science. The problem was simple to state, but nearly impossible to solve. How does a gunner on the ground or aboard a ship hit an aircraft moving through 3-dimensional space at speeds that made accurate prediction effectively impossible with the technology available in the early 1940s? December 7, 1941, had demonstrated this problem with brutal clarity. Pearl Harbor, on the island of Oahu, suffered under the weight of Japanese aerial attack that Sunday morning. As Japanese aircraft screamed through tropical skies heavy with humidity and smoke, American gun crews fought back with everything available in their arsenals. 5-inch naval guns thundered from damaged ships still settling into harbor mud, hurling shells skyward at attacking dive bombers and torpedo planes that seemed to fill the sky above Battleship Row. Each shell required manual fuse setting before loading, a process where a sailor turned a wrench against a clockwork mechanism while enemy aircraft dove through defensive fire that more often than not missed completely. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late, the shrapnel falling uselessly into water or fields far from any target. Some shells never exploded at all, their fuses failing to function or damaged during firing. Others fell back to Earth with their contact fuses still armed, creating a secondary threat that military planners had not anticipated when designing defensive systems for harbor protection. In Honolulu, 9 miles distant from the harbor where ships burned and men died, Shells weighing 55 pounds crashed through roofs of civilian homes, detonated in streets where families had been walking to Sunday services, tore through buildings where people sheltered from the attack. The Hirosaki family died together when a 5-inch shell flew through their restaurant window during breakfast service that morning. Father Jitsuo Hirosaki, his sons Jackie and Robert, daughter Shirley, and his nephew George all perished instantly, along with 7 young men who had been eating breakfast at the Cherry Blossom restaurant when American anti-aircraft fire fell onto their neighborhood. 3-year-old Janet Yumiko Ota became the youngest casualty of American defensive fire when a shell struck her family's home, killing her, her mother, and her aunt in an instant of explosion and flame. By the time smoke cleared over Pearl Harbor that afternoon, revealing the full extent of damage to the Pacific Fleet, 68 civilians lay dead in Honolulu and surrounding areas. 32 of them had been killed in Honolulu specifically, not by Japanese bombs or strafing attacks, but by improperly fused American anti-aircraft shells that had fallen back to Earth and detonated in neighborhoods miles from their intended targets. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft operating in conditions that made accurate fire control nearly impossible. The mathematics were unforgiving and had been since the first anti-aircraft guns were deployed during the Great War. Traditional anti-aircraft fire required 3 pieces of perfect information executed in precise sequence under combat conditions that made precision effectively impossible. First, optical rangefinders had to calculate exact distance to a target moving at speeds approaching 300 miles per hour, potentially through smoke, clouds, or the glare of tropical sun reflecting off water. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will, changing their position relative to predicted paths. Third, fire control computers, mechanical devices that represented the cutting edge of calculating technology in 1941, had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude and cross the distance to its target. A sailor then manually set a clockwork time fuse based on these calculations, turning the mechanism to the calculated number of seconds before the shell would reach the predicted intercept point. The shell was loaded into the gun, the weapon was fired, and the fuse mechanism counted down as the shell arced through the sky. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly despite the enormous forces of launch acceleration, the shell would explode near the target. The odds of actually destroying an aircraft under ideal conditions were approximately 1 in 2,500 rounds fired. In combat, with multiple targets maneuvering through defensive fire, with smoke and weather obscuring observation, with the stress of battle affecting calculations, the odds dropped catastrophically lower. The problem had existed since aircraft first became military threats during the First World War, but had become increasingly critical as aircraft evolved from slow biplanes into fast monoplane fighters and bombers. In 1918, aircraft flew at 90 miles per hour at altitudes rarely exceeding 10,000 feet. By 1941, fighters could reach speeds of 400 miles per hour and operate at altitudes above 30,000 feet. The gap between gunnery technology and aerial performance had widened into a chasm that threatened to make anti-aircraft defense effectively impossible. The British had discovered this reality facing German dive bombers during the evacuation of Dunkirk in 1940, where ships packed with soldiers attempting to escape destruction found their anti-aircraft defences woefully inadequate against determined aerial attack. Ships lacked space for additional guns beyond what they already carried. More ammunition consumed limited magazine space needed for other ordnance. Better fire control helped marginally, but could not overcome the fundamental limitation of time fuses that required perfect prediction of an aircraft's future position seconds into the future. August 1940 brought a potential solution to attention in Washington. The Department of Terrestrial Magnetism, part of the Carnegie Institution in the nation's capital, housed laboratories where Dr. Merle Anthony Tuve conducted research into fundamental physics, Born in South Dakota and educated at the University of Minnesota and Johns Hopkins, Tuve had spent his professional career exploring the physics of the ionosphere using radio waves to probe the upper atmosphere. In 1925, working with Gregory Bright, he had pioneered techniques for measuring the reflection of radio waves from the ionosphere to map its structure and behavior. This work had laid theoretical foundations that would later prove essential for radar development. When representatives from the National Defense Research Committee approached him in August 1940 about developing a proximity fuse for artillery shells, Tuve understood immediately that radio physics might provide the solution to a problem that had defied conventional approaches. The British had already conducted preliminary research and shared their findings during the TESAD mission, a transfer of technology between allies that included radar developments and other secret weapons research. British scientists had concluded that while a proximity fuse might theoretically work in rockets or bombs, the enormous forces involved in artillery launch made it impossible to construct electronic devices that could survive. A 5-inch shell experienced acceleration of 20,000 times the force of gravity when fired from a naval gun. No electronic device known in 1940 could survive such forces. Certainly not the delicate vacuum tubes that formed the only available electronic amplifying components. Tuve proposed something radically different from previous approaches. A miniature radio transmitter and receiver, no larger than a pint milk bottle, would be installed in the nose of an artillery shell. The transmitter would broadcast radio waves continuously as the shell flew through the air. As the shell approached a target, radio waves would reflect back from the aircraft's metal structure. The frequency of the reflected signal would shift due to the Doppler effect, the same physical principle that causes a train whistle to change pitch as it approaches and then recedes. When the frequency shift reached a predetermined level indicating proximity to the target, an electronic circuit would close, sending electrical current to a detonator that would explode the main charge and destroy the aircraft. Simple in concept, straightforward in theory. Absolutely impossible in execution given the technology available in 1940, or so conventional wisdom insisted. The project, designated Section T of the National Defense Research Committee, began formally on August 24, 1940, with Tuve serving as chairman and a handful of researchers working in laboratories at the Carnegie Institution. Security surrounded the project from the beginning, with researchers instructed to discuss their work with no one outside the program. Their first challenge involved identifying what components a working fuse would require and what specifications those components must meet. A radio transmitter capable of operating at frequencies that would provide usable Doppler shift from aircraft-sized targets. A receiver sensitive enough to detect reflected signals from an aircraft several hundred feet away, despite the tiny fraction of transmitted power that would reflect back. An electronic amplifier to boost the received signal to levels sufficient for detection. A circuit to compare transmitted and received frequencies and detect Doppler shift indicating approach to a target. A power source that could provide sufficient voltage and current to operate all electronic components. A detonator triggered by the electronic circuit. Safety mechanisms to prevent premature detonation during handling, loading, or launch. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter, the size constraint imposed by the nose section of a 5-inch naval shell. Every component presented problems that seemed insurmountable to engineers accustomed to conventional electronics. Vacuum tubes, the only electronic amplifying devices available in 1940, consisted of fragile glass envelopes containing delicate filaments and electrodes that glowed when heated by electrical current. Standard radio tubes stood 6 inches tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand perhaps 10 times the force of gravity during rough handling or vehicle operation. The proximity fuse required tubes that could survive 20,000 times the force of gravity during the fraction of a second it took the shell to travel down a gun barrel. At 20,000 times gravity, a 1-ounce vacuum tube would effectively weigh 1,250 pounds for the brief moment of acceleration. Forces sufficient to turn solid steel into fragments, to compress metal into different shapes, to destroy anything not specifically designed to survive. No vacuum tube in existence could survive such conditions. October 1940 saw laboratories across America receiving urgent requests from the National Defense Research Committee. Western Electric Company in New York and Radio Corporation of America in New Jersey were asked to develop miniaturized vacuum tubes hardened for extreme acceleration beyond anything previously attempted. Sylvania began developing specialized glass formulations that might survive forces that shattered conventional glass instantly. Raytheon experimented with tube designs featuring planar electrodes that distributed forces more evenly across internal structures. Engineers discovered through testing that conventional assembly techniques produced tubes that shattered instantly under high acceleration, with glass envelopes rupturing and internal components fragmenting. The solution required fundamental innovations in every aspect of tube design and manufacturing, from the glass composition to the methods used to seal components inside the vacuum envelope. Glass was modified with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Internal components were embedded in shock-absorbing materials that cushioned them against acceleration forces. Electrode structures were redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress that would tear apart conventionally assembled components. By spring 1941, after thousands of design iterations and countless failed prototypes, acceptable vacuum tubes emerged from production lines. These tubes measured less than an inch in height, no larger than a person's thumb, and testing demonstrated they could survive 20,000 times the force of gravity without failure. The success represented a breakthrough in electronics manufacturing that would have applications far beyond proximity fuses, though no one involved in the project recognized this broader significance at the time. The power source presented equally daunting challenges that required solutions as innovative as the vacuum tube developments. Harry Diamond and Wilbur Hinman, working at the National Bureau of Standards, developed an ingenious approach that solved multiple problems simultaneously. They designed a battery consisting of a glass tube filled with electrolyte solution and sealed with metal plates at each end. When the shell sat at rest in storage or handling, the liquid remained in the center of the tube, isolated from the metal plates by the glass structure. Chemical reaction could not occur because the electrolyte never contacted the metal plates. When fired, centrifugal force from the shell's rapid spin forced the electrolyte outward against small pieces of metal embedded in the tube walls, bringing the chemicals into contact with the metal plates. Chemical reaction between the electrolyte and metal plates generated electrical current sufficient to power the electronic components. The battery activated only when the shell was spinning at high speed, providing a built-in safety mechanism that prevented premature detonation during handling or accidental drops. The design was elegant in its simplicity and absolutely reliable in operation. October 6, 1941, marked a crucial test at the Dahlgren Naval Proving Ground in Virginia. 6 prototype fuses built by the National Bureau of Standards team were loaded into bombs and dropped from aircraft over water. Radio transmitters activated as the bombs fell. Receivers detected reflections from the water's surface approaching rapidly. Electronic circuits triggered detonators at the calculated altitude. All 6 bombs exploded at the correct height above the water, demonstrating that the basic concept functioned exactly as theory predicted. The success validated fundamental principles, but bombs experienced only a few hundred times the force of gravity when released from aircraft, nothing like the forces that artillery shells endured. Artillery presented a challenge 2 orders of magnitude greater, requiring components and assemblies that could survive forces far beyond what the bomb tests had demonstrated. By June 1941, Section T had expanded dramatically from its modest beginnings. Over 100 engineers, physicists, and ordnance specialists now worked on various aspects of fuse development. a former automobile dealership in Silver Spring, Maryland, became the main laboratory facility, chosen for its large open spaces that could accommodate testing equipment and its location convenient to Washington. Security surrounding the facility was so tight that neighbors speculated endlessly about the mysterious activities behind blackout curtains and locked doors. The cover story described research into optical instruments for military applications, plausible enough to deflect casual curiosity, but vague enough to prevent detailed questions. The reality behind those walls was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war by making aerial attack against ships prohibitively costly for enemy forces. The development process revealed a cascade of engineering challenges that had to be solved sequentially, with each solution enabling progress on subsequent problems. The antenna had to be small enough to fit in the nose of a shell, while remaining efficient enough to transmit and receive radio signals with sufficient power and sensitivity. Engineers developed a ring antenna that circled the fuse body, maximizing effective size while fitting within dimensional constraints. The transmitter circuit had to generate radio frequency signals at 70 to 90 MHz, frequencies chosen to provide useful Doppler shifts from targets at ranges of several hundred feet. Circuit designers created transmitter designs using just 3 miniature vacuum tubes, each one representing months of development work to perfect reliability under extreme conditions. The receiver circuit had to detect signals 1/1,000,000th the strength of the transmitted signal, amplifying these incredibly weak reflected signals 2 levels sufficient for processing. Amplifier stages using 4 vacuum tubes provided sufficient gain while remaining simple enough for reliable mass production. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the frequency difference indicated proximity to a target at the optimal distance for maximum fragment effectiveness. This circuit represented the heart of the fuse, the component that transformed radio signals into the decision to detonate. December 1941 transformed the proximity fuse project from important research into critical national priority. The attack on Pearl Harbor demonstrated with devastating clarity the inadequacy of time fuses against modern aerial attack. The Navy, which had been skeptical that electronics could survive gun launch despite encouraging test results, witnessed firsthand during the Pearl Harbor attack. How ineffective conventional anti-aircraft fire proved against determined attackers. All doubts evaporated in the smoke over Battleship Row. Production contracts expanded from millions of dollars to hundreds of millions as the program shifted from development to mass production. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942. Specifically to centralize proximity fuse development and provide coordination for the expanding program. 5 major companies received contracts to mass-produce fuses following designs developed at the Applied Physics Laboratory. Crossley Corporation in Cincinnati, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris, each committed entire factories to fuse production, converting facilities that had manufactured radios or cameras or automotive parts into assembly lines producing proximity fuses. Over 100 additional factories would ultimately participate in the program, producing components for fuses that each contained approximately 130 miniaturized parts. The production goal was 40,000 complete fuses per day by late 1943, increasing to 70,000 per day by war's end. Meeting these targets required industrial coordination on a scale rarely attempted, even during wartime mobilization. The secrecy surrounding the project remained absolute as production ramped up. Workers assembling components were never told what the final product would do or how it functioned. Different companies manufactured different sub-assemblies, with no single facility except final assembly plants having access to complete fuses. The designation variable time fuse was chosen specifically to mislead anyone who might learn of the project into thinking it represented some kind of improved mechanical timer. The code word POZIT was used in military communications, meaningless to anyone not cleared into the program. Even after combat use began in early 1943, captured fuses that failed to detonate and fell intact were assumed by enemy intelligence services to be some kind of advanced time fuse. Japanese and German technical analysis of captured examples never determined the true nature of the technology, partly because the concept seemed impossible given known electronics capabilities. August 12, 1942, saw comprehensive testing at sea. The cruiser USS Cleveland conducted trials with production proximity fuses against radio-controlled drone aircraft launched to simulate aerial attacks. 3 target drones were launched to create realistic scenarios. Cleveland's 5-inch guns, firing proximity-fused ammunition, required fewer than 10 rounds to destroy all 3 aircraft on the first day of testing. The results so exceeded expectations that naval authorities cancelled the remainder of the scheduled 2-day test program and immediately authorized mass production and fleet deployment. In comparative tests conducted over the previous 2 years using conventional time-fused shells, gun crews scored hits requiring an average of 2 1,500 rounds fired per aircraft destroyed under ideal conditions. Proximity-fused shells destroyed aircraft with dramatically fewer rounds, demonstrating effectiveness 25 times better than conventional ammunition. The improvement represented a revolution in anti-aircraft capability. Production accelerated through fall 1942 as factories ramped up output and supply chains matured. The first combat-ready proximity fuses reached fleet units in the Pacific during October. The cruiser Helena, operating with task forces in the Solomon Islands, received 500 rounds of proximity-fused 5-inch ammunition in late December. The ammunition was carefully distributed throughout the ship's magazines to prevent accidental disclosure of the technology if the ship suffered damage that might allow enemy forces to recover intact examples. Instructions distributed to gun crews emphasized that proximity fuses were to be used only over water, where duds would sink beyond enemy recovery. Gunners received training in handling and loading procedures, but were deliberately not told how the fuses functioned or what made them different from conventional ammunition. Initial fleet reaction ranged from skepticism about new untested technology to curiosity about weapons that reportedly performed far better than existing ammunition. The morning of January 5, 1943, resolved all doubt among those who witnessed it. Lieutenant Cochrane's salvos from Helena destroyed 1 Japanese dive bomber outright and damaged a second sufficiently that it crashed attempting to return to base. The gun crews aboard Helena had achieved aerial kills without perfect prediction of target position, without manual fuse setting based on complex calculations, without any of the elaborate procedures that had limited anti-aircraft effectiveness since its inception. Word spread through the Pacific Fleet with remarkable speed. Within days, every ship that had received proximity fuses was using them in every engagement with enemy aircraft. Cruisers, destroyers, and battleships reported kill ratios far exceeding anything achieved with time fuses under comparable circumstances. Enemy pilots began noticing that something fundamental had changed in American anti-aircraft defenses, but could not identify what specifically made American ships so much more effective. By March 1943, approximately 25% of all anti-aircraft ammunition issued to Pacific Fleet units contained proximity fuses, with the remainder being conventional time-fused shells. Despite representing only a quarter of ammunition expended, proximity-fused rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire during this period. Statistical analysis demonstrated that proximity fuses proved approximately 3 times more effective per round than conventional time fuses against comparable targets. Japanese pilots adapted their tactics in response to increased American effectiveness without understanding its source. Low-altitude torpedo bombers had traditionally approached at wave-top altitude for final attack runs, but proximity fuses proved less effective in this regime because radio reflections from the ocean surface often caused premature detonations before shells reached optimal range. Japanese aviators increased their use of these low approaches, though this exposed them to shorter-range automatic weapons fire that proved equally deadly. Dive bombers modified their attacks to use steeper angles and released bombs at higher altitudes to minimize time exposed to anti-aircraft fire. These adaptations reduced Japanese strike effectiveness while failing to restore the tactical advantage they had enjoyed earlier in the war when American defenses were less capable. American ships continued shooting down Japanese aircraft at rates that made conventional attacks increasingly unsustainable for Japanese naval aviation already suffering heavy losses to carrier-based fighters. Admiral William Halsey, commanding South Pacific forces, credited proximity fuses with fundamentally changing the balance of aerial combat. Japanese torpedo bombers had been particularly effective in night attacks when visual tracking was nearly impossible, and time fuses were essentially useless due to difficulty estimating range and altitude in darkness. With radar detection providing tracking data and proximity fuses, eliminating the need for precise fuse timing, ships could engage aircraft effectively even in total darkness. During 1943, despite using proximity fuses in only 25% of ammunition expended, over half of all Japanese aircraft destroyed by anti-aircraft fire were killed by proximity-fused shells. The disparity demonstrated effectiveness that exceeded even optimistic pre-deployment predictions. October 1944 brought a new phase to the Pacific War as American forces returned to the Philippines. Japanese forces, facing inevitable defeat as American military power overwhelmed defensive positions, implemented a strategy that would test American defenses to their absolute limits. Special attack units, officially termed Shimpu Tokubetsu Kogeki Tai, but known universally by the term kamikaze, meaning divine wind, began conducting deliberate suicide attacks against American ships. The first organized kamikaze attacks struck during the Battle of Leyte Gulf in October 1944. The tactic emerged from desperation and Japanese recognition that conventional attacks had become ineffective against American defenses that now routinely destroyed attacking aircraft before they could deliver weapons. Experienced pilots who knew how to conduct effective bombing and torpedo attacks had been systematically destroyed over 2 years of attrition warfare. Replacement pilots received minimal training, barely sufficient to fly aircraft competently, insufficient for the precision required in conventional attacks. Kamikaze attacks required only enough skill to keep an aircraft pointed at a target until impact. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the fundamental nature of the threat. Conventional aerial attacks saw aircraft approach, release weapons, and attempt to escape back to their bases. Proximity fuses destroyed attackers at distances where damaged aircraft would veer off course and miss their targets. Kamikaze attacks eliminated the escape phase entirely. Pilots flying damaged aircraft, sometimes with one wing torn away or control surfaces destroyed, continued flying toward targets through sheer determination and the momentum of their aircraft. Even catastrophic damage that would cause conventional attackers to abort sometimes failed to prevent kamikazes from crashing into ships. The solution required concentration of fire that completely destroyed aircraft rather than merely damaging them sufficiently to force withdrawal. Ships increased rates of fire, creating denser patterns of proximity-fused shells, and engaged targets at longer ranges to allow more time for complete destruction before aircraft reached ships. The destroyer USS Hadley and destroyer escort USS Evans, operating as radar picket ships on May 11, 1945, faced 156 attacking aircraft during a sustained 90-minute engagement off Okinawa. Hadley destroyed 12 aircraft with anti-aircraft fire before being struck by 4 kamikazes that remained airborne long enough despite battle damage to crash into the ship. Evans destroyed 23 aircraft before suffering damage that forced her withdrawal from the picket line. Post-action analysis showed that proximity fuses had been indispensable in this engagement, destroying aircraft at ranges where time fuses would have been completely ineffective. Without proximity fuses providing the defensive capability they demonstrated that morning, both ships would certainly have been sunk within the first 30 minutes of the attack. Statistical analysis from the Pacific War documented proximity fuse effectiveness with precision that left no room for doubt about their value. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition under circumstances where analysis could isolate the weapon system responsible. Detailed studies by analysts, including Ralph Baldwin, showed that only 46 of these aircraft would have been destroyed using conventional time fuses under identical circumstances. The 6-to-1 effectiveness ratio translated directly into lives saved and ships kept operational. At Okinawa, where American ships faced the most intense and sustained kamikaze operations of the entire war, proximity fuses accounted for a significant percentage of Japanese aircraft destroyed before reaching their targets, though the majority of aerial kills still came from combat air patrols flying protective missions over the fleet and from shorter-range automatic weapons that destroyed aircraft within a few thousand yards of ships. June 12, 1944, opened a new chapter in proximity fuse history as the technology moved from naval warfare in the Pacific to European skies. While proximity fuses had revolutionized naval anti-aircraft defense, strict restrictions had prevented their use over land where unexploded fuses might fall into enemy hands and reveal their secrets through technical analysis. German technical intelligence had proven highly capable of reverse engineering captured Allied equipment, understanding operational principles from physical examination. The Vergeltungswaffe one flying bomb campaign against London forced reconsideration of these restrictions. Beginning June 13, 1944, Germany launched thousands of pilotless cruise missiles at England, with over 120 per day during peak periods of the assault. Traditional anti-aircraft defences struggled desperately against targets travelling at 400 miles per hour at altitudes below 2,000 feet, where conventional gun-laying techniques proved inadequate. Winston Churchill personally authorized use of proximity fuses against flying bombs despite the substantial risk of technology disclosure. The threat to London demanded acceptance of risks that would have been unacceptable under other circumstances. Modified fuses optimized for the specific characteristics of flying bomb interception were rushed into production at Crosley Corporation facilities and flown across the Atlantic by special Lancaster bomber flights operating at maximum range. British 3.7-inch and American 90mm anti-aircraft guns deployed in defensive belts south of London began firing proximity-fused ammunition against incoming flying bombs in mid-July 1944. The effect was immediate and overwhelming beyond even optimistic predictions. During the first week of operations with the new ammunition, kill rates increased from 10% of incoming flying bombs to 24%. By the fourth week, after gun crews gained experience and defensive positions were optimized, 79% of flying bombs detected approaching London were destroyed by proximity-fused anti-aircraft fire. On a single day toward the end of the flying bomb campaign, radar stations detected 104 missiles approaching England's capital. Proximity-fused anti-aircraft guns destroyed 68 before they could reach populated areas. Fighter aircraft, which had been achieving modest success through dangerous pursuit tactics, destroyed 32 of the remaining missiles. Only 4 reached London to impact in areas where they killed civilians and destroyed property. The British capital was saved by technology developed thousands of miles away, specifically to protect American ships from Japanese aircraft. December 16, 1944, brought proximity fuses into ground combat under circumstances that would demonstrate new applications of the technology. German forces launched their final major offensive in the west, attacking through the Ardennes forest in Belgium and Luxembourg through terrain that Allied planners had considered impassable for armour. The attack that would become known as the Battle of the Bulge caught American forces by surprise during weather that grounded air support and allowed German columns to advance rapidly through broken defensive lines. Colonel George Axelson, commanding the 406th Artillery Group defending Monschau, Germany, made an unauthorized decision that morning. Facing massed German infantry assault against his positions, he ordered his artillery crews to load proximity fuses and fire them in ground combat mode despite strict prohibitions against land use that remained in effect. The emergency, Axelson decided, trumped peacetime restrictions. His guns opened fire with airbursts that devastated attacking German formations. 3 days later, on December 19th, General Dwight Eisenhower, commanding Allied forces in Europe, formally requested authorization from Washington to employ proximity fuses in ground operations throughout the theatre. All restrictions were removed on December 21, 1944, as the magnitude of the German offensive became clear. The effect on German forces proved catastrophic beyond anything experienced previously. Traditional artillery fired shells that buried themselves in mud or snow before exploding, directing most explosive energy downward into the ground and severely limiting fragment distribution across the surface where enemy troops were located. Proximity-fused shells detonated 20 to 50 feet above ground level, showering fragments over areas 50 times larger than conventional ground-burst shells covered. Each airburst created lethal fragment patterns covering over 3,000 square feet compared to approximately 60 square feet for conventional shells. German infantry advancing through open areas toward American positions found themselves subjected to airbursts that no foxhole or trench could provide protection against. Fragments rained down from above, penetrating helmets and striking soldiers in positions that would have provided complete protection from conventional artillery fire. The psychological effect proved nearly as devastating as the physical casualties. General George Patton, whose Third Army received priority allocation of proximity-fused ammunition as it drove north to relieve Bastogne, documented the devastating effectiveness in reports to higher command. On the night of December 25th, American artillery caught a German battalion attempting to cross the Sauer River near Echternach under cover of darkness. A single American artillery battalion firing proximity-fused shells killed 702 German soldiers by actual count conducted after American forces secured the area. Bodies lay in patterns that clearly showed the overhead burst nature of the shells. Patton wrote enthusiastically to the War Department about the new ammunition. "The shell with the funny fuse is devastating," he reported. "We caught a German battalion trying to cross the Sauer River with a battalion concentration and killed by actual count 702 men. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." Between December 1944 and March 1945, from the initial German offensive through final Allied crossing of the Rhine River, American artillery equipped with proximity fuses achieved results that exceeded anything possible with conventional ammunition. Proximity-fused shells calibrated for airburst detonation took fearful tolls on German forces attempting to maneuver or defend positions. Advanced fire control radar enabled American artillerymen to deliver precision fires on targets located on reverse slopes of hills and beneath forest canopy, situations where conventional direct-fire weapons were completely ineffective. The Germans captured approximately 20,000 proximity fuses when they overran an American ammunition dump during the initial offensive. German ordnance experts examined the captured fuses carefully, conducting detailed technical analysis to understand their function. The conclusions reached by German engineers revealed how completely the concept exceeded contemporary understanding of what was possible. German analysts concluded that the fuses could not possibly function as intended based on examination of their construction. The technical specifications seemed impossible given known limitations of electronics and materials. Electronics that could survive artillery launch forces were considered completely beyond current technology by German experts who were themselves at the forefront of weapons development. The Germans assumed the fuses represented some kind of advanced mechanical time mechanism they did not fully understand. The fuses were carefully warehoused for potential future study and eventually abandoned as German forces retreated eastward in the face of Allied advances. The secret remained secure throughout the war, not primarily through security measures, though those were extensive, but through enemy disbelief that the technology could actually exist and function as designed. March 1945 saw proximity fuses adapted for yet another application. American forces preparing to assault the heavily defended island of Iwo Jima faced concentrated anti-aircraft batteries and shore defense positions that would inflict heavy casualties during landing operations. Proximity fuses were modified for installation in bombs dropped from aircraft, calibrated to detonate several feet above ground to create airbursts over enemy positions. The modification required only minor changes to fuse circuitry to adjust detonation altitude. B-24. Liberator bombers attacked Japanese positions with proximity-fused bombs in the days preceding the Marine landings. The airbursts proved devastating against dug-in defensive positions, destroying equipment and killing defenders in fortifications that would have survived conventional bombing. The technology that had been developed to protect ships from aircraft had evolved into a general-purpose weapon effective in almost any situation where explosive ordnance was employed. The industrial achievement behind proximity fuse production equaled or exceeded the technical accomplishment of initial development. The supply chain ultimately involved 87 firms operating 110 factories across America. Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris served as primary assembly contractors, coordinating efforts of over 2,000 suppliers providing components. At peak production rates, the American electronics industry manufactured 70,000 proximity fuses daily, each one containing 130 precision components that had to function reliably under conditions that would destroy conventional electronics instantly. The cost per fuse dropped from $32 in 1942 to $18 by 1945 as production techniques improved, economies of scale reduced overhead, and workers gained proficiency in specialized assembly procedures. Secretary of the Navy James Forrestal stated after the war's conclusion that the proximity fuse helped blaze the trail to Japan, noting that without the protection this device provided to surface ships conducting operations increasingly close to Japanese home waters, the westward advance could not have proceeded so swiftly, and the cost in men and ships would have been immeasurably greater than even the heavy toll actually paid. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitchell, commanding fast carrier task forces during operations against Japan, recalled in post-war interviews that by 1945, essentially all 5-inch anti-aircraft ammunition carried by fleet units was fitted with proximity fuses, and those fuses knocked down enemy aircraft by the dozens, preventing ship losses and casualties that would have been enormously larger without this technology protecting American vessels. Winston Churchill noted in his post-war memoirs that proximity fuses manufactured in America proved potent against the flying bombs that assailed Britain during 1944, providing defensive capability that saved countless civilian lives in London and other targeted cities. The Japanese never fully understood during the war why American anti-aircraft effectiveness had increased so dramatically after early 1943. Post-war interrogations of Japanese military officials revealed that most believed Americans had developed vastly superior fire control radar systems, or had somehow integrated aircraft detection with gun directors in ways Japan could not duplicate with available technology and manufacturing capacity. Some Japanese engineers speculated about the possibility of radio-controlled shells, but the concept was dismissed as technically impossible given the extreme forces involved in gun launch that would destroy any electronics. The idea that individual artillery shells could carry miniaturized radar systems capable of detecting targets and timing their own detonation seemed beyond credible technology, even to engineers who were themselves developing advanced weapons. This fundamental failure of imagination, shared by German technical intelligence services, allowed the proximity fuse to remain operationally secret throughout the entire war, despite thousands of intact examples falling into enemy hands. The human cost of Japanese failure to develop equivalent technology proved substantial. Japanese naval aviation lost over 12,000 aircraft in combat during the war across all theaters of operation. Documented evidence and statistical analysis show that proximity fuses accounted directly for several hundred of these aircraft destroyed through anti-aircraft fire, with thousands more damaged sufficiently to crash before returning to bases or carriers. Each aircraft destroyed represented not just material loss that Japanese industry could not adequately replace, but trained aircrew who were literally irreplaceable given the time required for pilot training. The death of experienced pilots during 1943 and 1944 forced Japan to commit poorly trained replacement pilots who fell victim to American defenses at unsustainable rates that destroyed Japanese naval aviation as an effective fighting force. By 1945, Japan resorted increasingly to kamikaze tactics, partly because conventional attack methods had proven ineffective against American ships equipped with proximity-fused ammunition and sophisticated defensive systems. The broader impact of proximity-fused technology extended far beyond World War II into post-war military development that continues influencing weapons design into the present era. The techniques developed for miniaturizing electronics and hardening components to survive high acceleration became foundational knowledge for subsequent technological advances. Missile guidance systems that enable precision strike against targets thousands of miles distant. Space exploration requiring electronics that function reliably after launch acceleration. Modern artillery that achieves precision through course-correcting fuses, all benefited from innovations pioneered by the Proximity Fuse Development Program. The concept of distributed intelligence, where individual munitions carry sophisticated sensors and processors enabling autonomous operation, traces directly to principles established by VT fuses. Modern smart munitions that can sense targets independently, discriminate between legitimate targets and protected objects, and optimize detonation timing represent evolutionary development of principles first demonstrated operationally between 1943 and 1945 in the Pacific. Dr. Merle Tuve, returning to the Carnegie Institution after the war concluded, rarely spoke publicly about his central role developing proximity fuses. When details of the program were finally declassified and released to public knowledge, Tuve consistently deflected personal credit, emphasizing instead the contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses that functioned flawlessly under impossible conditions. His modesty understated his essential leadership in a program that War Department officials ranked second only to the atomic bomb in strategic importance. Without his insight that radio proximity detection could be miniaturized sufficiently for installation in artillery shells, without his persistence through early failures. When success seemed impossible and skeptics advocated abandoning the entire concept, the proximity fuse would likely have remained a theoretical curiosity rather than combat reality that saved thousands of American lives and fundamentally altered tactical calculations throughout multiple theaters of war. The production achievement equaled the technical accomplishment in scale and complexity. Manufacturing 22 million proximity fuses over the course of production, each one containing 130 precision components machined to tolerances measured in thousandths of an inch, required industrial organization on unprecedented scale even during a period of massive wartime mobilization. Over 100 factories had to coordinate delivery of components matching specifications that allowed no deviation. Supply chains had to deliver vacuum tubes, batteries, detonators, and hundreds of other electronic and mechanical components from specialized suppliers scattered across the country, all synchronized precisely to keep assembly lines operating at capacity without interruption. At 70,000 fuses produced daily during peak output, the program required manufacture of approximately 9 million individual components every single day, or approximately 9 billion total components over the course of the war. The scale of production exceeded that of many much larger weapons systems, while maintaining quality standards that permitted almost no defects. The proximity fuse stands alongside radar, penicillin, and perhaps a handful of other technologies as having materially affected World War II's outcome through advantages conferred on Allied forces. Unlike radar, whose development occurred independently in multiple countries with similar technologies emerging from parallel research efforts, the proximity fuse resulted from deliberate application of existing scientific knowledge to a specific military problem. Dr. Tuve and his team at Section T identified clearly what needed to be accomplished, determined systematically how to accomplish it, and executed a development program that achieved operational capability in under 3 years from initial concept to combat deployment. This focused approach to weapons development became the organizational model for Cold War military research that followed. The Manhattan Project developing atomic weapons followed similar patterns of university laboratories conducting fundamental research, industrial contractors handling production engineering, and military oversight ensuring alignment with operational requirements. Post-war missile programs adopted this same basic structure. The legacy of those miniaturized electronics surviving 20,000 times, gravity extends beyond immediate combat effectiveness into fundamental changes in how modern nations organize scientific talent for military objectives, how industries manufacture precision electronics at scales enabling mass deployment, and how seemingly impossible technical challenges yield to sustained effort backed by adequate resources and competent leadership. The miniaturized vacuum tubes that seemed completely impossible in 1940 became routine production items by 1945. The precision manufacturing techniques that initially required specialized technicians became increasingly automated as production processes matured and engineering understanding deepened. But during 1943, 1944, and 1945, as Japanese aircraft fell from Pacific skies in unprecedented numbers, as German infantry died under artillery airbursts that no defensive position could protect against, as flying bombs disintegrated over the English Channel short of their intended targets, the proximity fuse represented the absolute cutting edge of what human technological capability could achieve through sustained effort. Lieutenant Red Cochrane, standing at his post aboard Helena, watching that first Japanese dive bomber disintegrate on the morning of January 5, 1943, understood in that moment that something fundamental had changed in the nature of aerial combat. His gun crew had just destroyed an enemy aircraft without perfect aim, without precise fuse setting calculated by mechanical computers, without any of the elaborate procedures that had limited anti-aircraft effectiveness throughout military history. The shell itself had done the work, sensing the approaching target through radio waves, calculating optimal detonation distance through electronic circuits, timing its own explosion to maximize destructive effect, achieving with autonomous operation what human gunners could only approximate through skill and luck. In that engagement off Guadalcanal, witnessed by men who barely understood the technology they wielded, a new era in warfare had announced itself. The age when individual munitions carried sufficient intelligence for autonomous operation had arrived. The implications would reshape military technology for generations. The proximity fuse proved definitively that sometimes the greatest victories come not through overwhelming force applied with crude instruments, but through scientific method applied systematically to the brutal realities of modern warfare, transforming theoretical physics into operational weapons that enemies cannot effectively counter because they cannot believe such technology exists. The German soldiers who faced artillery airbursts and Japanese airmen who flew against proximity-fused naval guns never fully understood what killed them with such devastating effectiveness. They reported only that American defenses had become impossibly accurate, that ships seemed able to shoot down aircraft regardless of evasive maneuvers, that artillery created explosions seeking targets with what seemed like supernatural precision. None recognized that they faced autonomous weapons making independent decisions about when to detonate for maximum effect. The proximity fuse did not win